Hello, my name is Jason Zane, and this is my Oscillations lab for Physics 2211. The purpose of this lab is to analyze the motion of a spring mass system and then compare it with a computational model to determine whether this model follows the energy principle. First, we will analyze the motion of the mass by using tracker. Next, we will use this data to calculate the spring constant and create a computational model using script. And here's a preview of our main result. We see that the change in kinetic, gravitational potential, and spring potential energy all add up to zero. This means that our model does indeed follow the energy principle. Two of the fundamental physics principles which are relevant to this lab include the energy principle, which states that the change in energy of a system is equal to its change in thermal energy plus the work done by its surroundings. And of course, we will also include Newton's second law. Remember that in an isolated system, the total change in energy is equal to zero. We will also need the formulas for kinetic, gravitational potential, and spring potential energy, as well as the formulas for gravitational force, Hooke's law, position update, and velocity update, all of which can be derived from Newton's second law. Here's a quick video of the observed motion from the tracker data. As we can see from the graphs on the right, we are observing oscillatory motion. For our models, we will be assuming the following. Our systems include the mass, spring, and earth only. And we will also assume that we have an isolated system, meaning that there will be nothing doing work upon our system. And finally, we will assume that the spring is perfectly elastic. In other words, it is an ideal spring. For our initial conditions, we are given the mass of the ball, which is 0.402 kilograms, and by setting the origin at the fixed position, at the fixed position of the spring, we get the following for the initial position of the ball. Next, we can use the tracker data to find the average period of the spring mass system, which is about 1.524 seconds. And this allows us to solve for K in the formula for the period of oscillation, giving us a spring constant of 6.83 newtons per meter. And finally, we can use Hooke's law to find the spring's resting length, which is about 0.125 meters. Next, I will explain the script portion of this lab. Once again, we see our initial conditions as we implement it inside of script. Here we are calculating the spring's stretch, direction, and compression length initially. Next, we are calculating the system's kinetic, gravitational potential, and spring potential energies before the spring is set into motion. Now, there's a lot going on inside the while loop, so I'm just going to briefly explain the process. Here, we are simply defining the initial energies of our system at the start of each iteration. Now we will use the gravitational force and Hooke's law to calculate the net force acting upon the system. Of course, we'll also have our velocity and position update formulas, and we will continue to update the spring at each iteration. And finally, we will calculate the change in kinetic, gravitational potential, and spring potential energy of the system. This will allow us to calculate the total change in energy of the system and see if energy is conserved. Thanks to all of our hard work in script, we can now see a comparison between our computational model and tracker data. Notice that the two graphs start off with a lot of overlap and then slowly start to deviate from one another as time goes on. This is likely due to the fact that our system is not actually isolated. There will always be non-conservative forces like air resistance, so energy will be lost from our system. And here is script's graph of our system's change in energy. As we can see, all of the changes in the different types of energies in our system add up to give us zero. This means that for our computation model, the energy principle is satisfied. Now, there were two ways we could have measured our period. The first way is to use the graph of the x position as a function of time. Doing it this way, we see that we get an average period of 1.714 seconds. The second way to find the period is what I chose for this lab. By using the graph modeling the y position as a function of time, doing it this way, we get an average period of 1.524 seconds. This shows that the direction we choose for calculating the period of oscillation matters. And finally, some potential errors which could have impacted our results include the following. Our experiment does not actually represent an isolated system because there will always be non-conservative forces such as air resistance doing work on our system. And also there's human error in plotting the tracker data, which is inevitable, and this could lead to inaccurate calculations of the period and thereby affecting our calculations for the spring constant and closed grip model. Thank you.